Hello everyone, I am Ansh and today I am going to represent my project EcoBreathe. The aim of the project is to improve air quality in dimly lit, cramped office spaces with no natural light and poor ventilation. This system, called EcoBreathe, utilizes sensors to monitor and regulate CO2 levels and employs activated carbon filter in the roots of the snake plant to enhance indoor air quality. Its goal is to create a more positive and lively work environment, promoting better health and productivity in spaces of around 100 to 200 square feet with a user friendly plug and play setup. The requirements of the project are really simple. It requires two AQI sensors for calculating CO2, VOC, PM1, PM2.5, and PM10 values. A microcontroller used Arduino Nano 33 IoT to control the pump and send and receive data values to the cloud. A Raspberry Pi acting as a server with GUI interface for user interaction. Hi guys, this is my project EcoBreathe. What it basically does is that it purifies the air naturally using the snake plant right here. The mechanism is that the air is sucked inside the snake plant's roots through the soil. It passes through the duct inside and gets exhausted out from here through the fan. It uses a carbon filter that is placed inside here. It has activated carbon in it. It is used to act as a catalyst for the air purification. Here is the water pump that is used to automate the system. Uh, this plant is totally self-sustainable. The water is pulled out from here directly up to here and is given to the plant. A soil moisture sensor that we use it is placed inside the plant here, like this. This sensor gives the data to the Arduino Nano 33 IoT that has to be connected here, and it uses this data to check if the soil has enough moisture, and if the soil is lacking moisture levels, then the pump is turned on by sending a signal from the Arduino. The pump is automatic, so it will remain on until the soil required soil moisture level is reached. What it basically does is that it gives the data signal and the pump releases water on the plant. The water is taken out from this part, this water container, and this is the PMS sensor, PM2.5 sensor from here right now. This sensor right here is the AQI sensor. It gives VOC and CO2 values. These are the pump options for the GUI interface as shown. The pump can be automated and manually controlled. Firstly, it is automated and the sensor is providing data. Right now the pump is on because the sensor is kept out to give fake values. Now the pump is operated manually. Now the pump is off. As soon as we turn the pump on, it it will turn on without taking the data from the sensor. We are still getting the live data, but it is not connected to the pump right now. As soon as we hit the on button, the pump is turned on. This right here is the Arduino code and the database, Firebase Cloud database that receives the sensor values. This data is further shown in the GUI interface using this Python script right here. This is the GUI interface and it asks for the admin username and password. As soon as we hit the login button, here we have the previous data, live data, and the pump options. First, we will see the live data. This is the live data of the CO2, VOC, PM1, PM2.5, and PM10 values right from the sensor. And the moisture is from the soil moisture sensor, and the water level is the amount of water present in the container. It gives the value of 1 and 0. Like if the water is present, the value is 1, otherwise, the sensor gives the value of 0.
Hello everyone, this is the code explanation of my task. First, we include the libraries. There are several libraries for various sensors and communication modules. The code is designed to work with DF Robot ENS160, Firebase, PMS, and Wi-Fi communication via the Wi-Fi Nina library. Arduino HTTP client is included for HTTP communication. Here is an instance of the DF Robot ENS160 sensor created with the I2C address 0 into 53. The PMS sensor is initialized with serial 1 for communication and a data object for PMS data is defined. Constants are defined for the analog pin used to read soil moisture A2. The digital pin is used to read an indicator signal on pin 9 and the digital pin used to control a relay on pin 2. Next, these lines define constants for the Firebase real-time database URL and secret key, as well as the Wi-Fi network SSID and password. A Wi-Fi client object is created for network communication. Here, the host name for IFTTT server is defined, along with specific path and query parameters to send a request to a custom webhook. We have used IFTTT to send an email to the user when the quantity of the container containing the water gets low. In the further lines, an instance of the Firebase data class is created for working with Firebase. The water level low flag is used to keep track of the water level state. Then comes the setup function. Here we have begun the serial monitor at 9600 baud rate and it is used for debugging purposes and communication with the PMS sensor. Pins are configured for input and output. The relay is set as an output and the indicator is set as an input. The soil moisture is also set as an input. Then a loop checks the connection with the DFS robot ENS160 sensor that measures CO2 and VOC. If there is any error, it displays a message and waits for 3 seconds before trying again. Here the sensor's power mode is set and it is also receives the value of temperature and humidity that it uses for to give accurate values. Then in the code it tries to connect to the Wi-Fi network. Until it is connected, it keeps printing on dots. When the network is connected successfully, uh, the code displays the local IP address and initiates a connection to Firebase using the provided database URL and security key. The setup function initializes various components including sensors, pins, and Wi-Fi connectivity. It also connects Firebase and IFTTT, setting up the environment for data collection and communication. The water IFTTT function is responsible for making an HTTP request to an IFTTT webhook. This part of the code establishes a connection to the IFTTT server maker.ifttt.com on the port 80. It uses the client object, which is a Wi-Fi client instance created earlier. Here, this line 69, this line tries to establish a connection to the IFTTT server. If the connection is successful, it returns true and the code enters the if block. If the connection fails, it returns false and the code enters the else block. After successfully connecting to the server, the code proceeds to send an HTTP GET request to the IFTTT webhook. This line right here, line 76, constructs an HTTP GET request. It includes the path and a query parameter. The HTTP uh, version is specified at the end of the request. The next line specifies the host header in the HTTP request, which is sent to the server. The next part of the code waits for a response from the IFTTT server. This line sets up a loop that continues as long as the connection to the server is still open. If there is incoming data, this line reads a character from the server's response and stores it in the variable C. The received characters are printed to the serial monitor. Now here comes the loop function. The loop function starts by checking if the PMS uh, read data function call returns true. The function is responsible for reading data from a particulate matter sensor PMS. If data is successfully read, the code inside the if block will execute. The code prints the concentration of particulate matter with a diameter of 1.0 micrometers in micrograms per cubic meter to the serial monitor. Similarly, the data of particles of diameter 2.5 and diameter 10 is printed. Then the code retrieves the operating status of ENS 160 sensor and prints it to the serial monitor. The status is stored in the variable status. In the next part, it retrieves the AQI air quality index from the ENS 160 sensor and prints it to the serial monitor. The AQI is stored in AQI variable. Next, the code obtains the concentration of TVOC, total volatile organic compounds, from the ENS 160 sensor and prints it into the serial monitor in parts per billion, and the data is stored in the variable. The next part fetches the carbon dioxide equivalent ECO2 concentration from the ENS sensor and prints it to the serial monitor in parts per million. The value is stored in ECO2 variable. These two lines help to get the sensor data from the soil moisture defined at pin soil moisture as defined earlier and the level indicator. This section here checks the water level indicator. If the level is low, indicating low water level, and the water level low flag is not set, it calls the water IFTTT function, which sends a request to an IFTTT server. It also sets the flag to prevent repeated triggers. If the water level goes back to high, the flag is reset. The code prints the values for water level and soil moisture to the serial monitor for debugging and monitoring purposes. This section retrieves data from a Firebase real-time database using the Firebase library. It retrieves the mode and pump values from specific paths and stores them in the mode and pump variables for later use. Next, the code checks the mod value. If the mode is automatic, it proceeds to control a relay based on the moisture level and water level indicator. If the moisture is above 480 and the water level is high, the relay is set to high. If the moisture is below 480 or the water level is low, the relay is set to low. The third condition ensures that the relay is also set to low if both moisture and water level are below their respective thresholds. If the mode is manual, the code checks the pump value. If pump is on, it sets the relay to high, and if the pump is off, it sets the relay to low. This part of the code constructs a JSON string with sensor data including AQI, PVOC, ECO2, particulate matter values, soil moisture, and water level. The data is formatted as a JSON string. Then the code attempts to send the JSON data to Firebase using the Firebase setJSON method. If the data is successfully sent, it prints a success method to the serial monitor. If there is an error, it prints an error message along with the reason of the error. Finally, after processing and sending the data, the code adds a delay of 1 second before the loop iteration repeats. This is the code for the GUI interface, which is made in the Python language in the Raspberry Pi server. We start by importing the tkinter library, which is a popular Python library for creating graphical user interfaces. Then we import message box module from tkinter that allows us to create pop-up message boxes. Then we import the Pyri-base library used for interacting with Firebase. Uh, then we import the time library. Then we have a configuration dictionary as defined, which contains the Firebase project configuration uh, information such as the API key, project ID, and database URL. We initialize a Firebase app using the provided configuration. We create a reference to the Firebase real-time database, which allows us to interact with it. Then we have a Boolean variable sensing enabled that is set to true. Next, we create the main window of our GUI application using tkinter. The title of the window is login form, and we specify its size, that is 800 into 600 pixels, and have set the background color to dark gray. Then we have defined a function that is responsible for fetching and displaying live sensor data from Firebase. We retrieve the data EQI, air quality index value, from the Firebase and store it in the variable EQI value. The same is done for other sensor data like ECO2, TVOC values, and more. We update the text of a label to display the EQI value, and similar updates are made for other labels displaying the sensor data. This all the data is this function runs every 1 second to continuously update and display the sensor data in the GUI. Then we have defined a function pump option that is called when the user selects an option for controlling the pump. It checks if the user has selected the automate option for the pump control. If automate is selected, a message box is displayed with information about the pump operation mode. The mode of pump is set to automatic in the Firebase database. If in automatic mode, the sensing button is hidden from the GUI. The option 2 is similar but is for the manual pump control. We define a function toggle pump option for showing or hiding the pump control options. It checks if the pump control frame is currently visible. If it is visible, the frame is hidden using pack forget method. The as block shows the pump control frame using this line if it's not currently visible. Then we have defined the login function that will be responsible for handling the login process. We have set a hard-coded username for login and a password. This line here checks whether the username and password entered by the user matches the predefined values. If the login is successful, the line displays an information message box with the title login success and success message. Uh, if the login is successful, this function create main page is used to create the main page of the application. This line right here, frame.packForget, is used to clear the login page. Then the mainframe statement declares mainframe as a variable as a global so that it can be accessed and modified in different functions. Its background is set to dark gray. Then this code creates three buttons: a previous data button, live data, and pump button for different actions in the main page. These buttons are styled with background colors, text, and font settings. These lines right here are used to center the button in a vertical position, and then it is displayed and expanded to fill the available space. The Open Live Data Page function is responsible for creating and displaying the live data page. It sets up labels to show sensor data, uh, retrieves actual data using the retrieve and display live data function, that is right here, and provides a close button to exit this page. Uh, the labels are initially loaded with loading to be updated with real data once it's available. The expand is equal to true. The expand is equal to true is ensures that the frame takes up the entire available space in the GUI. Next, we come up to the close live data page. It is similar as the previous functionality. It hides the current page that is in view, like for example the live data page, and shows the main page that had three options earlier. The close live data page function does a similar functionality as told earlier. It will hide this page that is currently in view, and it will show the main page. The pump data page function. First, we initialize the pump frame as a global variable. Then we create a new frame for pump options page with the background color set to dark gray. A label named pump label is created within the pump frame. It displays the text pump options with the styling. Next, the line specifies the grid layout for the pump label. Two radio buttons, automate and manual, are created using tkinter.radio function. These radio buttons allow the user to select between automate and manual pump options. The pump pair right here is a shared variable that keep tracks of the selected option. Then a sensing button variable is made. It is a global variable. It is used to control the state of the pump, whether it is on or off. A submit pump option button is created. When the button is clicked, it calls the pump options function. A close button is created. When this button is clicked, it calls the close pump data page function. Then we come to the toggle data sensing function. This function uses conditional statement to update the text and appearance of the sensing button based on the current state. It also updates the corresponding values in the Firebase database to reflect the new state of pump on or off. Then we create the widgets for the login form. The line creates a name. The line creates a frame named frame with a background color of dark gray. The frame is essentially a container for various widgets that will make up the login form. Then they create a widget for application name, EcoBreathe, team's name, the techmates, and the title of the login page, login to proceed. These labels provide headings and titles for the login form. Then these lines create entry widget for entering the username and password. The show parameter is used to mask the characters in the password field with asterisks for security. Then the line creates a login button that user can click to initiate the login process. The command is equal to login parameter specifies that the login function will be called when the button is clicked. Then these lines are used for placing the widgets on the screen, the exact location using the grid, where to place the buttons, labels, and entry boxes. The last line is used to expand the GUI so that it fills in the complete space, and it starts the GUI application's main event loop, which listens for users' interactions and keep the application running. This code sets up the basic structure of a login form using tkinter library. It creates labels for headings and titles, entry widgets for username and password input, and a login button. The row widgets and the use of the grid method arrange these elements within the frame, and the main loop function keeps the application running and responsive to user action.